Gasoline is the fuel that powers this modern age. On the highway, on the farm, and in the air. This is the inside story of modern gasoline. It's a big story, but it starts with something so small that no man has ever seen one: the carbon atom.
Hello, folks. I'm a carbon atom, and since I'm an essential part of each of the hydrocarbons in crude oil, I'm here to give you the inside dope on gasoline. I'm the smallest possible particle of carbon. Why, I'm so small, 1,000 billion atoms like me could dance on the head of a pin. Scientists know I act as though I had 4 arms, and these fellows, who are the hydrogen members of this combination, have only 1 arm. We're going to form a molecule. Watch. I grab hold of hydrogens like this, then another carbon. In doing this, we make a kind of chain. See? When we're together, the combination is a hydrocarbon molecule, one of the many, many different hydrocarbons. For instance, we have formed a typical gasoline molecule. Now I want you to meet some of my relatives who form in the same way but have different patterns.
I'm another hydrocarbon, a gas molecule.
My size makes me a typical kerosene molecule. I'm one of the fuel oil molecules.
A light lubricating oil molecule. That's me.
I'm a heavy lubricating oil molecule.
All of these carbons and hydrogens make me a residual materials molecule.
So you see, there are lots of different molecules, different sizes, different shapes, all found in crude oil.
Crude oil is still the best raw material for today's great motor fuels. In modern refineries, science builds gasolines from selected groups of molecules by changing their sizes, shapes, and structures. To do this job calls for great storage tanks. Batteries of pumps. A maze of valves and pipes. Mighty facilities. And an army of experienced, specially trained workers. The first step is to separate the crude oil into the parts that you saw a moment ago. This is done by distillation. You know that when you boil water, the vapors can be condensed. The same principle is used in distilling crude oil. Giant units with bubble towers condense vapors just as the cold tumbler did. Here in a single tower, much simplified, crude oil is separated into the different fractions needed for gasoline, kerosene, fuel oil, and other petroleum products. Here we see the crude oil being heated. Most of it is vaporized. At the bottom of the bubble tower, unvaporized large molecules of heavy lube oil and residual materials are drawn off. At the second level, the light lube oil is condensed out of the vapor and withdrawn. At the third level, the largest of the lighter remaining molecules condense to form the fuel oil cut. At the fourth level, kerosene is condensed and drawn off. At the fifth level, the gasoline molecules become liquid, leaving the very light gas molecules to go out the top of the bubble tower. In the average crude oil, only a limited amount of gasoline is present. So let's see what we might get from this simple distillation. A barrel of crude oil produces 20% residual fuel oil and asphalt, 7% lube oil and wax, 39% gas oil and fuel oil, 15% kerosene, 1% gas, and gasoline only 18%. Not nearly enough for today's millions of cars. But science came to the rescue by inventing the cracking process, enabling refiners to make more than twice as much gasoline from each barrel of crude. Today, were it not for the demands for fuel oil and diesel fuel, almost the whole barrel could be converted into gasoline. By making more gasoline, cracking has conserved our natural resources and at the same time made gasolines of higher anti-knock quality for greater performance and economy. Here's a typical gas oil molecule to be cracked. You're already familiar with the way it's constructed. To crack it, heat is applied under precisely controlled conditions, more heat than is needed for distillation. You're watching how science first changed a molecule into more useful one. On the left are two gasoline molecules. On the right are gas and carbon, all obtained from cracking one gas oil molecule. Thus, science first created gasoline where none existed before, high anti-knock gasoline. Here is one of the great units that produce gasoline molecules by cracking tens of thousands of barrels of gasoline each day. Several other science fashioning processes have since been developed. One is called polymerization. It simply takes similar type molecules that are too small for gasoline, such as these gas molecules, unites them by the polymerization process to form a larger molecule, a gasoline molecule of exceptionally high anti-knock value. Thus, science again fashions for us more and better products. By a somewhat different process, this alkylation unit joins together two very small molecules to make another high-octane gasoline component. And this reforming unit takes low-grade gasoline found in crude oil and changes it to high-grade gasoline. In many of these processes, and in the latest cracking process, the science fashioning is accomplished by a catalyst, a material that promotes reactions of other substances. The most modern cracking process uses a catalyst in the form of a fine powder that will flow like a fluid. Here is what happens inside a fluid catalytic cracker. Gas oil is heated. It is joined by the hot, finely powdered catalyst, shown here as little white grains. The hot oil and the still hotter catalyst then move together through pipes up into a chamber called the reactor and are tumbled about. Here, the heavy oil molecules are cracked by catalytic action to produce gasoline molecules. These move out at the top. As the catalyst becomes covered with coke, it becomes less active and is drawn off at the bottom. Air blows it through a pipe to the regenerator where the coke is burned off. This reheats the catalyst, which again joins the flow of incoming oil. Here's the entire operation, showing the complete cycle. Notice that the same catalyst is used over and over in this modern method of gasoline manufacture. It takes a complicated unit to do the job. Every 2 minutes, a whole carload of catalyst passes through the lines. 16 stories high, each of these big cat crackers can produce enough gasoline in one day to last the average motorist 1,000 years. Contrast the modern unit you've just seen with this historic Burton cracking still at Whiting, Indiana. the first successful commercial cracking unit. Though the amount of oil in today's catalytic cracking units is actually less than in the old Burton units, the catalyst cracks the gas oil more than 7,000 times faster and so permits much greater throughput. It is one more demonstration of serving through science. The average driver may not know a cat cracker from a firecracker, but he wants top performance when he starts the engine. The right volatility allows the engine to warm up without coughing or sputtering. But starting and warm-up are not the whole story. In all seasons, the driver wants quick acceleration and a lot of other things. He wants full power on the highway. He wants long mileage and economy. And all of these things call for a scientific balance of gasoline components. You know how easy it is to ignite gas, which is made up of small molecules. Here's a mixture of liquid hydrocarbons so light and volatile that the heat of a hand will make it boil. It's flammable, and so volatile it ignites fast. Now, here are some of the heavier, less volatile hydrocarbons. The lighted taper does not ignite them. Yet, when vaporized and burned in an engine, they pack a lot of power and give mileage. To make a gasoline blend that will have a proper combination of volatility characteristics, first we put in the very light hydrocarbons for quick starting. The next heavier ones have rapid warm-up. Then some that give instant live power acceleration. And a final portion for full power and good mileage out on the highway. The blended gasoline has the desired range of performance with economy because it contains just the right groups of hydrocarbon molecules. One for instant starting, but so active that in the summer it should be used only in moderation. One for rapid warm-up. One for smooth acceleration. And one for full power and good mileage. Molecules that work together. A harmonious team. In the engine laboratory, by means of a glass intake manifold, you can actually see one of the volatility differences between fuels. Slowing down the action, here's what too low volatility causes: a wet manifold and imperfect distribution. These liquid droplets decrease engine performance, waste mileage, and dilute the crankcase oil. By switching to a fuel with correct volatility, vaporization is complete and there is no waste. Building trouble-free performance starts in the laboratory, but it doesn't stop there. Fuels are tested under all kinds of road conditions, in all types of engines, and under all the different seasonal and climatic conditions. This means city driving. It also means rolling out into the country, driving at moderate temperatures and in hot weather and in extremely cold weather. Seasonal variations and the climates of different regions must be taken into account. Volatility is adjusted to suit the season and the region in which the gasolines will be used. A distillation test measures the volatility of motor gasoline. This is the test which determines how the various components of the gasoline have been blended. But volatility is only one major requirement. What about this? Listen. Fuel knot that needs to be prevented. Let's go back to the laboratory and get this part of the story.
The motorist wants smooth, controlled application of power. Using a special demonstrator, I shall show the difference between poor performance and good performance. Now, with the hard face of this mallet, I strike the piston. The piston, you see, receives a punishing rap, showing how power is wasted when gasoline knocks. This time, I shall use the cushion face of the mallet to show what happens when gasoline does not knock. smooth, useful power propels the piston, sends the crank spinning. The performance difference you've seen is a mighty important one that you ought to understand better. So let's look inside the engine by means of animation and see what happens when the fuel burns. These gasoline molecules have not been improved on or controlled by science. They are untamed and unruly. What you will see next actually takes place in about 1/500th of a second. First, the spark ignites the compressed fuel charge. Now, watch for the knock. In this greatly slowed down action, you could see that with this gasoline, combustion was uneven and uncontrolled, and at the end there was a jarring, violent explosion, a knock that pounded and shook the engine. Now, with gasoline made up of molecules that have been science-fashioned so that they have the required anti-knock quality, molecules that stay under control and work as a team, let's see what happens. Note in this case that the combustion is more uniform, and there is no knock. The big difference, as you could see, is that with gasoline of the required anti-knock quality, there is no knock. Combustion is smooth and even and completely under control. In the modern high-compression engine, modern gasoline gives the greater performance required today. The car accelerates more rapidly, climbs hills faster, travels more miles per gallon. In addition to fashioning the molecules to prevent fuel knock, refineries usually add minute quantities of tetraethyl lead to help accomplish the same purpose. This model shows how just the right amount of fluid containing tetraethyl lead and dye is added to the gasoline. In the knock testing laboratories, test engines are used to make sure that the proper anti-knock quality has been built into modern gasoline. The high anti-knock reference fuel is called iso-octane, hence the expression octane number. This test engine is equipped with a dial indicator that shows just how badly the engine is knocking. With a fuel of low octane number, here's how it sounds. Switching to a high octane number fuel, the knocking diminishes and finally fades out completely. This illustrates the smooth, even performance you get from a fuel of proper anti-knock quality.
All of these facilities and know-how are not enough. There must be safeguards, the constant protection of every necessary control test. For example, the vapor pressure test that controls vapor lock tendencies. A test to make sure there is no harmful gum. Another to make sure that today's fine gasolines will not deteriorate in storage. A test that guards against corrosive impurities. Testing, testing. Behind the top performance of today's fuels are more than 1,500 daily control tests. But what about tomorrow's fuels, the fuels of the future? Let's visit another of the great laboratories. This one is entirely devoted to extensive research into the changing world of tomorrow, 10 years from tomorrow, even into the next century. Here are some of the country's most capable scientists, and hundreds of men like these are also working on more and better products. Cooperative work with the automobile industry guarantees that exactly the right gasoline will be available for each new engine as it comes on the market. Engine design changes are studied. Perhaps more critical fuel requirements and new operating problems are found. The progressive gasoline refiner may discover a need to change his basic fuel components or provide new ones in order to meet the new requirements. He may also discover a need to employ special additives. Such additives, expertly blended in, are capable of doing some things that gasoline alone cannot do. They already are contributing importantly to the building of today's fine fuels. Similar new developments may contribute much more in the future. It takes all this and more to build today's great motor fuels, while steadily developing the power and the performance for tomorrow's engines. One of the latest achievements in gasoline science fashioning is catalytic reforming. It uses a platinum-containing catalyst. Step by step, unit by unit, the art of science fashioning is advanced, continuing progress that has become a tradition in the industry.
So there's the story, folks, and I'm proud to be a part of it, even if only as a tiny atom inside modern gasoline.
Now you know something of the great story behind the gasoline you use, whether it's delivered to you on a farm or on the driveway of a service station. Another fine example of serving through science.